Question 2. 2 is all about isomers. Isomers. So the first one we have cis and trans, geometric isomers around a square planar nickel 2 D8 center. These geometric isomers. B. This is all about what is bound to the metal. So it's a slightly sneaky one. Do you have a cobalt bromine bond? Or do you have a cobalt, I guess it'll be the oxygen of sulfate bond like that? Precisely which ligand is bound to the metal, that's the form of isomerism there. Tina Overton's textbook is excellent on the isomers. I do suggest you explore this if you're struggling with isomerism. C. These are geometric isomers again. So these are the Fac and Mer isomers. Do those three identical ligands sit along some sort of meridian, like the prime meridian on a globe, or do they sit on the face of an octahedron? Do they sit in a little triangle, if you like, trans to the other type of ligand? D is quite a fun one. Let's have a new page. Let's do that. So there's a few things happening in D. The first one I want to talk about is the optical isomerism, which is possibly the harder one. When those chloride ligands are cis to each other. So when there is a 90-degree angle between those chloride ligands. These N ligands, ethylene diamine, they sort of have to be cis to each other because of this organic bridge between them. This molecule here has an enantiomeric pair, a mirror image which is not superimposable, with this structure here. These are enantiomers. This is optical isomerism. Yep, that's how you do an A. There, good. There is, though, another type of isomerism in this molecule, and that's, well, what if these chloride ligands are not cis to each other? What if they are trans to each other? In that case, you would have a different molecule. So let's have these chloride ligands out the side. These bidentate N ligands along, if you like, the sort of waist of the molecule. And this will be a geometric isomer to those two structures I just drew out. A geometric isomer. So this molecular formula, this complex, has three possible arrangements of atoms. Three distinct molecular forms. Three isomers. E one is an example of linkage isomerism. And the key idea here is, well, which atom in the NO2 ligand binds? Is it the oxygen, or is it the nitrogen? This is linkage isomerism. Oh, I've moved everything. No. There we go. Linkage isomerism. And again, Weller, the Overton Weller, Armstrong and Rourke book. That's the one you want if you are struggling with isomers. It's really good, very clear. So we're nearly there. Question 3. Arguably this isn't what I've taught you at all. This kind of synoptic assessment, looking back at stuff you've already learned, is enormously important in your education, so no regrets here from me. Let's just make sure we're able to do it. So we've done some analysis on a molecule. We've worked out the mass due to each group, if you like. So the chromium has some mass associated. These chlorine atoms have some associated mass. And the data given describes ammonia, some extra component of this molecule. We've got the percentages here. Let me copy them over. We've got 24.9. We have 50.7. And we have 24.4. As chemists, we don't really mind what mass things are. We really want to know about the sort of number of moles. So what we want to compare these percentages to is, I guess, the relative molecular mass of each of these fragments. So we can look on our periodic table, which you will have in your exam, and we see chromium has an atomic mass of 51.9961 on my periodic table. That's a 6 there. Should we do that one again? That's 6 there. Yeah. Smooth. 9961. Oh well. Chlorine, whatever could the atomic mass be? I have on my periodic table 35.4527. A balance of those lovely chlorine 35 and 37 isotopes. And ammonia. I'm going to take hydrogen as 1. I don't like counting. I'm going to take nitrogen as 14. So I'm going to call this 17. And neglect those decimal places. So then we can do a simple division to see what molar fraction of the composition is made up by each of these components. So we can divide 24.9 by 51.99. It's going to give us a new number. Let's do it. 24.9, 51.9961. I'm going to save that in my calculator as A, but the number is about 0.479. We can do the same for chlorine here. We can take 50.7 and we can divide it by 35.4527, and we get a number that's something like 1.430. And we can do it finally for ammonia. We can take 24.4, divide it by that lovely round number 17, and we get 1.435, which I'll save as C. We can then look at these ratios and divide by the smallest one. So this gives us some feel for the whole number ratios of these systems. So this is the smallest anyway. There's going to be 1 chromium atom per empirical formula unit, which seems reasonable. 1 metal atom in the middle of a complex. Sure, I can get behind that. But we take 1.435 0.43, and we divide that by 0.479. We get 2.99. Looks a lot like three chloride ligands. Yeah, I could believe that. And if we take 1.435, we divide that by our smallest number, we get to 2 decimal places, 3.00. So that's good. What we found then is we have a chromium atom, we have 3 chloride ligands, and we have 3 coordinated ammonia molecules. This will give us the lovely geometric isomers, these FACMER isomers that we touched on earlier. That's a satisfying little question. Very well set, I think. 3A is just an encouragement to go back to the books. Please use the books. Books are the way you master this topic. You master my lecture course. Please use them, please. I look forward to seeing you in workshops. Bye-bye for now.